Hi, in this video we will look at sampling in base nets. I'll step through a few examples of sampling from just a regular joint distribution you're provided with, a conditional distribution, and then we'll look at various base net sampling methods. We'll start with sampling from a joint distribution, in this case a distribution over variable. In this case, a distribution over a random variable a, which can take on two values, plus a and minus a. Our sampling procedures go in two steps. In the first step, we sample uniformly at random from the 0-1 interval. Typically, most programming environments will provide this functionality to you, and then your job is to go from this functionality to having the functionality of being able to sample from arbitrary distributions. For example, this distribution shown over here and distributions we will look at in future slides. In step 2, we then generate the samples from the requested sample distribution. The way this is done is by first mapping the provided distribution onto the 0-1 interval. So we look at 0-1. We step through this distribution, first row, plus a, 0.8 probability. So from 0 through 0.8, we assign plus a. Then the second row, 0.2 probability for minus a. So from 0.8 through 0.8 plus 0.2, which is 1.0, we have minus a. To generate the samples, we now map these intermediary samples over here onto the 0-1 interval and back out the values for a. The first one gives us plus a. The second one, 0.58, maps over here, also gives us plus a. Third one, 0.04, maps over here, that's also plus a. Fourth one, 0.94, maps over here, that's the minus a region, so we have a minus a. 0.67 maps over here, that's the plus a region. And then 0.49 maps over here, that's also the plus a region. So we have 5 times plus a, 1 times minus a. Now let's look at how this works for a distribution where we have a random variable that can take on more than two values. Again, we have two steps. In the first step, we draw uniformly at random from the 0-1 interval. This, again, is assumed to be provided by your programming environment. Then in step 2, we map this to samples from the target distribution, the distribution over A. To do this, we consider the 0-1 interval, and we map each of the entries of A onto a part of the 0-1 interval. We start with the first entry, A1, which has a probability of 0.35. So from 0 through 0.35, we have A1. We have a probability of 0.15 for the next one, A2. So from 0.35 through 0.5, we have A2. We have a probability of 0.1 for A3, which is the next one. So from 0.5 through 0.6, we have A3. Then we have a probability of 0.25 for A4. So from 0.6 through 0.85, we have A4. And then for the last one, A5, we have a probability of 0.15. So from 0.85 through 1, we have A5. Now proceeding with the sampling procedure, 0.31 maps onto the A1 interval, so that's A1, 0.58 maps onto the A3 interval, so we have A3, 0.04 maps onto the A1 interval, another A1, 0.94 maps onto the A5 interval, so that's A5, 0.67 maps onto the A4 interval, so that's A4, and 0.49 maps onto the A2 interval, so that's A2. We have 6 samples. We have twice A1, 1 time A2, 1 time A3, 1 time A4, 1 time A5. One question you might ask yourself, what if now the next one here had been 0.6? 0.6 would map right here on the boundary between A3 and A4. The way we assign when landing on the boundary is by assigning it to the next one. So in this case, we would have that 0.6 would map to A4. Now let's look at how to sample from a joint distribution. We now have two random variables. We have A and B. Now let's look at how to sample from a joint distribution. We now have two random variables, A and B, and this is their joint distribution over here. Again, we proceed according to the same two steps. First, sample uniformly at random from the 0-1 interval, and then we'll map that to samples from the target distribution. To get the samples from the target distribution, we map all entries in the target distribution to the 0-1 interval. In this case, again, we start with the first row, plus A plus B, with probability of 0.3, so the interval from 0 to 0.3 is assigned to plus A plus B. Next entry, plus A minus B, has a probability of 0.1, so from 0.3 through 0.4, we have plus A minus B. Next one, minus A plus B, a probability of 0.4, so from 0.4 through 0.8, we have minus A plus B. Last one, probability of 0.2, so from 0.8 through 1, we have minus A minus B. Now to generate our samples, we do the mapping from these intermediary samples onto the 0-1 interval. Now we'll generate our samples, 0.3 Now we'll generate our samples. 0.31 maps onto the plus A minus B interval. 0.58 maps onto the minus A plus B interval. 0.04 maps onto the plus A plus B interval. 0.94 maps onto the minus A minus B interval. 0.67 maps onto the minus A plus B interval. And 0.49 maps also onto the minus A plus B interval. So we have 3 times minus A plus B, 1 time minus A minus B, 1 time plus A plus B, 1 time plus A minus B. How about sampling from a conditional distribution? Well, it turns out, as posed for now, this is it. Well, how about sampling from a conditional distribution? Here is a conditional probability for B given A. How do we sample from this? Turns out we can't just directly sample from this. To sample from a conditional distribution, somebody needs to tell us what the value is of the conditional variable. So in this case, somebody would need to tell us what value A is taking on. Let's assume that person told us that A equals plus A. Now we can sample from the conditional distribution of B given A equals plus A. That corresponds to sampling from a distribution over B, where B takes on plus A and minus B with probability 0.3 and 0.7. So again, we would map that onto the 0-1 interval. Plus B goes from 0 through 0.3, and minus B goes from 0.3 through 1. To generate our samples, we first draw uniformly at random from the 0-1 interval, and then we map them onto this. And then we map them onto plus B and minus B. 0.31, that's minus B. 0.58, that's minus B. 0.04, that's plus B. 0.94, that's minus B. 0.67, that's minus B. 0.49, that's minus B. So we have 5 times minus B, 1 time plus B in this process here. Now let's consider sampling from a base net. Now let's consider sampling from a probability. Now let's consider sampling from a probability distribution that is provided to us in the form of a base net. As a reminder, a base net, we have a directed acyclic graph, and we have a set of conditional probability tables, one for each node in the graph. Each node in the graph corresponds to a random variable. One way to sample from this basenet is to first generate the full joint distribution, which is always possible when you're given a basenet, and then sample from that full joint distribution. We know how to sample from the full joint distribution. We've done that in the previous slides. Typically, however, that's not what you want to do. The reason you work with a basenet is because it gives you a more compact representation of a probability distribution. If you go back to the full joint distribution, you lose that compactness, and you get an exponential blow up in terms of and you often end up with an exponential blow up in terms of representation size, which ends up being very expensive. So what we'll look at now is ways of sampling from probability distributions that are specified as base nets without ever expanding into the full joint distribution, but by simply considering whatever. Again, we will rely on a set of random numbers that come from. Again, we will rely on a set of numbers generated uniformly at random from the 0-1 interval. And going forward, I will now assume that when you're given such a number, for example, given 0.31 and given a probability distribution, for example, probability distribution for A, that you know that this will map to plus A. If that's not clear, go back to the previous slides, watch the video again, and find out, make sure you understand why 0.31 would map to plus A, and for example, 0.94 would map to minus A. Okay, to sample from the base net, what we need is a ordering that's consistent with the directed acyclic graph. This directed acyclic graph has two orderings that are consistent with it. There is A, B, C, D, and there's also A, C, B, D. Both are equally consistent with the partial ordering provided by this directed acyclic graph. You can choose whichever one you want to work with. I'm going to work with the first one, A, B, C, D, but it's perfectly fine if you want to choose the second one. That's completely up to you. We'll work with ABCD to sample from this base net using forward sampling, which is often also known as prior sampling. We first sample the first variable in our ordering here, which is A. We look at the distribution for A. We look at the number over here, 0.31, that will map to plus A. We move on to B. The conditional distribution for B is given over here. There's a conditional distribution. We need to look at what the conditioning variable's value is. Conditional variable A is taking on plus A, so we're looking at this part of the table. We have 0.58 that will map to plus B. Moving on to C. Here's our conditional distribution for C. The conditioning variable A has been sampled as plus A, so we consider this part of the table over here. Our number 0.04 for this table here maps to plus C. Moving on to D, big table over here. Our conditioning variables B and C take on plus B and plus C. That means we're looking at this part of this conditional probability table. 0.94 will map to minus D. So our first sample has been generated. It's plus A plus B plus C minus D. Let's move on to the next sample. Again, we start with the first variable in our ordering, A. We have 0.67. 0.67 maps onto plus A. Moving on to B, the conditioning variable A is plus A, so it's this part of the table again. 0.49 maps onto plus B. Moving on to C, the conditional variable A is plus A, so again it's this part of the table to look at. 0.37 maps onto plus C. Moving on to D, we have for the conditioning variables plus B plus C, so it's again this same part of the table. 0.42 maps onto minus D. So our second sample is also plus A plus B plus C minus D. And then we can continue this for however many steps we'd like, depending on how many samples we want. We now know how to sample from a distribution specified just as a table or specified as a base net. Let's now take a look at what we can compute from these samples. In particular, how do we answer probabilistic inference queries based on samples that we got from the distribution? Here's the set of samples we assume we obtained from some distribution over A, B, C, and D. These are 10 total samples. And here's a set of queries we would like to answer about the joint distribution over A, B, and C. So these are queries about our sample distribution over these are queries about our distribution over A, B, C, and D, from which we sampled to get these samples here. The first thing to remember is that from samples we'll never compute an exact answer to these queries, so we'll always have approximate. The first thing to keep in mind is that samples will typically only give us approximate answers. So we never an exactly equal. So we won't put an exactly. So we will not put an exactly equal sign. We will not put an equal sign here, but an approximately equal sign. The way we estimate And the way we estimate, now let's see how we answer a particular query. What's the probability of plus d? Based on these samples, we're going to estimate that as the number of times we saw plus d divided by the number of samples. Number of times we have plus d is 1, 2, 3 times. The total number of samples is 10, so it's estimated as 3 over 10. Moving on to the next query, probability of plus a and minus b. Our estimate is the number of times we see plus a jointly with minus b divided by the total number of samples. Number of times we see plus a minus b is 1, 2, 3 times. So we have 3 over 10. Next one, the joint probability of minus a minus b minus c minus d. It's the number of times we see that joint instantiation, minus a minus b minus c minus d. Divided by the total number of samples. We see that joint instantiation once, so this probability is estimated as 1 over 10. Now we're switching gears and we're looking at conditional probability queries. Now we're switching gears and we're looking at conditional probability queries. The way we answer a query like this based on samples is as follows. The way we answer a query like this is, here is how we answer these types of queries. We estimate that probability as the number of times we saw the query and the evidence variables divided by the number of times we saw the evidence. So in this case, it's the number of times in the samples we see minus c and minus d divided by the number of times we saw minus d. Minus d appears 7 times. Minus c minus d appears 4 times. So our estimate is 4 over 7. Our next conditional probability query, again we answer this query. Again, we use as our estimate the number of times we see the joint instantiation of query and evidence variables divided by the number of times we see the evidence variables. We estimate this probability from samples as the number of times we see the particular instantiation of the query and evidence variables divided by the number of times we see that particular instantiation of the evidence variables. In this case, the number of times we have plus d minus a minus b divided by the number of times we have minus a minus b. Minus a minus b occurs over here and over here. That is twice. And plus d happens 1 out of those 2 times, so we estimate this probability as 1 over 2 based on these samples. Now, it is possible that from a given set of samples we cannot answer a certain probabilistic query. When will this happen? This happens when this will happen. So in general, when we're asked for the probability of a query variable instantiation given some evidence variable instantiation, it's going to be the number of times we saw the query and the evidence instantiation divided by the number of times we saw the evidence instantiation. If it happens to be the case that in our samples the number of times we saw the evidence is equal to 0, then also the number of times we saw the query jointly with the evidence will be 0, and we'll end up with a 0 over 0, which means we cannot estimate that conditional probability from the samples we've obtained so far. Note more generally, there's something interesting going on here. Whenever we are asked for a conditional probability query, the only samples that participate in this estimate are those samples that are consistent with the evidence. And so we Note that there's something interesting going on here. Whenever we're asked to answer conditional probability query, the samples that we care about are the ones that have the correct evidence instantiation. So we might want to ask ourselves the question, if we know the query in advance, and so we know what the evidence variable instantiation is, can we sample more efficiently such that we have more samples that have that right evidence instantiation? The answer is yes, and we're going to look at two approaches. The first one is called rejection sampling. The idea in rejection sampling is that you reject a sample once you realize that you sampled an evidence variable inconsistent with the instantiation that your query has. So if your query were the probability of some query variables given an evidence variable or several evidence, if your query was of the form probability of Q given E, once you sample one of the evidence variables in a way that's not consistent with the query instantiation, you stop working on that sample and move on to restart from the first variable in your basenet and try to generate a new sample. This can save you a lot of time. Imagine a very large basenet and Imagine a very large basenet and you start sampling and one of the first variables is an evidence variable and you sample it inconsistent with the evidence. You can now shortcut sampling all the other variables in the basenet because you know you're not going to use that sample anyway and right away move on to compute it, to use your compute power to try to compute a next sample that might be consistent with your evidence and so will be useful for answering your probabilistic query. Now there's one thing that might be a little unsatisfactory about this. Imagine a basenet where you're happily sampling lots and lots of variables and then you arrive all the way at the bottom of your basenet and there's an evidence variable there and you happen to sample that evidence variable inconsistent with your evidence. What now? Now you're rejecting that sample. You did a lot of work. You worked all the way through the basenet, sampled all these variables, and you end up rejecting the sample, not being able to use it. Likelihood weighting, which is the second approach, provides a remedy to that problem. Likelihood weighting, which is the second approach we're going to look at, provides a remedy to that problem. The idea in likelihood weighting is that rather than sampling the evidence, instead you force the evidence to be consistent. Instead, you force the evidence variables to be consistent with the evidence instantiation you are provided with. And then you reweight your samples to make sure that you are properly accounting for the conditional probability table of those evidence variables. Let's take a look at rejection sampling first. Let's take a look at rejection sampling first. Again, we will rely on a sequence of numbers generated uniformly at random. Okay, let's first take a look at rejection sampling, and we have a particular query here, the probability of minus d given minus b. We'll again rely on a set of numbers that we generate uniformly at random from the 0-1 interval. Rejection sampling proceeds like forward sampling, prior sampling, just whenever we encounter an evidence variable and we sample it inconsistent with the evidence instantiation in the query, we'll stop working on that sample. Okay, let's start. We'll take the ordering A, B, C, D. Again, you could pick A, C, B, D if you wanted to. Any ordering consistent with the DAG, any ordering consistent with this directed acyclic graph will do. Starting with A. A has this conditional, A has this table here. 0.31 will map onto plus A. Moving on to B. Moving on to B, we have a conditional probability table for B. The evidence variable A is set to plus A. So the evidence variable A was sampled as plus A, so we're looking at this part of the table. 0.58 will map onto plus B. B is an evidence variable. In the query, it's instantiated as minus B. So we sampled it wrong. That means we reject this sample, stop working on it, and move on to working on a new sample. So we again start with A. 0.04 maps onto plus A. Moving on to B. A is sampled as plus A, so we again look at this part of the table. 0.94 will map onto minus B. That's consistent with the evidence, so we keep going. C, the parent of C, A, is sampled as plus A, so it's this part of the conditional probability table. 0.67 will map onto plus C. Then D, D's table is over here. We have the parents of D, B, and C being minus B and plus C. That's this part of the table over here. 0.49 would map onto minus D. Note that D also appears in the query as minus D, but D appears as a query variable, and whenever it appears as a query variable, it doesn't matter what we sample it as, we always keep working. It's only when it appears as an evidence variable that we will reject if it's inconsistently sampled with the evidence. Moving on to the next one, we would now go again to A, B, and so forth, and we can generate as many samples as we like to estimate the requested probability. Now let's consider likelihood weighting. Our query is the probability of minus D given minus A and minus B. Again, we pick an ordering of variables consistent with directed acyclic graph. We'll work again with A, B, C, D, but if you wanted to work with A, C, B, D, that'd be equally good. Starting with A is an evidence variable. Likelihood weighting, that means we don't sample it, instead we force it to take on the value it has in the query, which is minus A. To account for the probability table for A, we now reweight the sample. Minus A had a probability of 0.2, so we have a reweighting by 0.2. Moving on to B. B is also an evidence variable, so B gets instantiated to minus B in this case. To account for the probability table for B, we look at the conditional. To account for the probability table for B, we will reweight the sample. The parent A was minus A, so it's this part of the table. B is forced to be minus B, so we get a reweighting by 0.5. We go on to C. C is not an evidence variable, so we just sample it. Here's our table for C. This will be the first variable we sample for this likelihood weighting execution. We have 0.31 as our first number. 0.31 will map to Next is C. C is not an evidence variable, so we'll sample it from its conditional probability table. The parent A has the value minus A, So we're going to look at this part of this conditional probability table here. 0.31 maps to this part here, which is giving us minus C. Moving on to D. D is not an evidence variable, so we sample it. Note that D does appear over here as minus D, but that doesn't matter in likelihood weighting. What matters is which variables appear as evidence variables. D does not appear as an evidence variable, just as a query variable. Since it doesn't appear as an evidence variable, we sample it. Sampling D, here's our table for D. The parents B and C take on the values minus B minus C. That means we are in this part of the table over here. 0.58 will map to plus D. Here's our first sample, minus A minus B minus C plus D, and it's weighted by the product of the reweightings. So we multiply all these reweightings together, giving us a total reweighting of 0.1. Let's do another one. We start at A. A is an evidence variable, so we instantiate it as minus A. We need to look at the reweighting in the table for A. It's a reweighting by 0.2. Moving on to B. B is an evidence variable. It's instantiated to minus B. We need to reweight. The table for B is over here. The parent for B is A. A takes on minus A, so it's this part of the table. We force it to be minus B, so we have a weighting factor of 0.5. Moving on to C. C is sampled because it's not an evidence variable. The parent of C, A, is minus A, so it's this part of the table again. We have 0.04. This maps to plus C. Moving on to D. The parents for D take... Moving on to D. D is not an evidence variable, so we sample it. The parents for D, B and C, take on the values minus B plus C. So we are in this part of the table here. 0.94 will map us on to minus D. So here's our second sample. It's minus A minus B plus C minus D, and it's reweighted by the product of all the reweighting that we have along the way, which gives us a reweighting by 0.1. And we'll keep working through the same procedure to generate however many samples we'd like to generate. One question you might have is, how many samples should we generate? When you do likelihood weighting, well, now let's take a look at how we can answer probabilistic queries from weighted samples. So we here have a set of weighted. Now let's take a look how we can answer probabilistic queries using weighted samples. We have some samples here that were drawn from a distribution P, A, B, C, D, and these samples have the following instantiations, and each of them has a weight, such as could happen. Now let's take a look at answering probabilistic queries from weighted samples that are drawn from a distribution over A, B, C, and D. Here's our first query. What's the probability of plus D? Again, we're estimating this from samples. We're not likely to get the exact answer here, so we put approximately equal sign. We estimate it as the The way we estimate this is as the sum over all samples. Let I index over the samples. I, there's 10 samples in this case, I from 1 to 10. The weight of that sample, Wi, times an indicator variable that takes on the value